Alright, I was explaining something and I ran out of battery, so I will continue with what I was saying. Given this equation, y of n is equal to x of n minus 1 times 1 minus e to the minus at plus y of n minus 1 e to the minus at, we want to draw out the block diagram of what this actually looks like. So this is x of n that goes into a multiplier, and this is the generic form of what I'm drawing, and I put this equation up here. This is the generic form of the transfer function that we want to achieve. So h of z is equal to the summation from I is equal to 0 to p, b of I, z of negative I, divided by 1 minus summation from j is equal to 1 to q of a of I to the z of negative j. Now please go back and check your notes and make sure that this negative sign is there. I think I wrote it on the board incorrectly. This negative sign makes it to where when you solve this out, you do the cross multiply, and then you add these terms to the other side, they come up to be positive coefficients because you're multiplying them over. This 1 is actually associated with the y of n, and then these terms all get subtracted over to the other side, so they become positive. So anyways, back to the hardware instantiation of this. X of n is going to go into a multiplier of b of 0, and this is going to go out and go into a summation block. X of n is also going to get tapped off and go through a z minus 1 block. This is a time delay. This time delay block is going to go down through another multiplier, and this is a b to the 1 multiplier, and goes into the summation block. And then on the other side, this is going to come out, and this is y of n. And y of n is tapped off and is delayed, z to the minus 1. And this comes through a multiplier. This is multiplied with a of 1, and then fed back into the summation block. So this is a multiply block down here at the bottom. Now, the assumption is always held that a of 0 is equal to 1, but I often like to explicitly write that. But a of 0 is equal to 1. A of 1 is defined here at the start. J of equal to 1, a of 1, and that is e to the negative at in our instance. Now the interesting thing though that we can look at with this, x of n normally goes through this multiplier b of 0. However, in our equation, we have no x of n. We only have an x of n minus 1. So what that does to this hardware instantiation, we're going to assume that this b of 0 is equal to 0. And so then we have x of n, and it no longer goes through this multiply block, because that says multiply by 0. It now goes to this z minus 1 block. And this z minus 1 block gets multiplied by the b of 1, and then for this particular example, there's no longer a summer. And it goes to the other side, the summation, and out for as y of n. Tapped off, goes through another delay block, gets multiplied by a of 1, and back into the summation block and out. So, when we do not have an a of n, we only have an a of n minus 1, you can see that this time delay block doesn't do anything, because this right-hand side only depends on the values that are being put through here. So because this is a time invariant system, it doesn't matter if we shift x of n forward or backward. So if we're looking at this system from the point of view with this guy as x of n, which is x of n minus 1, all the processing is still going to be the same, because all we've done is shift it 1. Because it is time invariant, we can do that. So we can rewrite this one more time and say x of n is going to go through a multiplier with b of 0, and this is going to go through a summation block. This is going to go to y of n, and this is going to go through a z to the minus 1 block, a multiplier, a of 1, back into the summation block. So if this is equal to 0, this and this is the same. If b of 1 is equal to, what do we have? 1 minus e to the minus at, and b of 1 is equal to 1 minus e to the minus at, and then we're reassigning b of 0 to now be 1 minus e to the minus at. So these are equivalent circuits. So that brings us back to the steps in our process. The last step, step number 5, is to add poles or zeros at z is equal to 0. So z is equal to 0 is to eliminate this standing z. To adjust the delay of the filter. So that's what it's talking about here. We can now add poles or zeros at z is equal to 0 to eliminate this guy in the numerator, because this and this are equivalent filters. So what that means, our final version of this filter is going to be h of z is going to be equal to, we get rid of this guy because he's not doing anything. We can do that as long as there is not a b0. And we can go on. If this is a z to the minus 2, that's the first thing we see in the numerator. We can get rid of 2 z's. Right? Okay, so h of z is now going to be equal to 1 minus e to the minus at divided by 1 minus e to the minus at. That is multiplied by z to the minus 1. This is in this form of the transfer function. Using this form, we can now define our constant variables, or our filter variables, which is b0 is going to be equal to 1 minus e to the minus at, a1, or I'm sorry, a0, let's explicitly state a0 is going to be equal to 1. That's this term right here, this term right here. And a1 is going to be equal to e to the minus at. And notice it is not negative e to the minus at, because we have this negative sign here. It is positive e to the minus at. So this completely defines our digital filter that we derived from pole zero matching from a continuous time filter. So let's do another example that's a little bit more complex. Let's say that we have a new transfer function. This new transfer function in continuous time is going to be equal to h of s, which is equal to s divided by s squared plus 0.2 s plus 1. Alright, in this one, we're going to say t is equal to 0.5 seconds. Alright? What type of filter is this? Second order on the denominator. We have an s in the numerator. From our knowledge of Bode plots, we can look at this and say, okay, this is a positive 20 dBs per decade, starting at omega is equal to 1, and it goes forever in both directions. This is a negative slope of negative 40 dB per decade that starts at omega of n, and omega of n is at, let's see, this is omega n squared. Is that right? So we know that this, if we just look at the Bode function for this, and let's say this is omega is equal to 1, and this is omega is equal to 0.1, we have the pole, or we have the 0 in the numerator, and then we have the second order, which is coming down at negative 40 dB per decade. So when these two sum together, we're going to get something. Then we need to put it in the standard form and get the DC, but I'm just giving a very rough approximation of what this looks like. It is going to come up here and go down here. So, given this, we know that it is a bandpass. So we're going to look at this bandpass filter, try to figure out how to convert it into the other domain. So, for this one, we can rewrite this, and we can say that the S, the poles of the S, the root of the denominator, is the poles at S is equal to negative 0.1 plus or minus J 0.995. So there's complex poles if we do a solution on the bottom. So now we can use the steps that we had from the previous. And the first thing is determine the poles and zeros of the H of S. We have a 0 at S is equal to 0. Alright, so step 1. Find poles, zeros of H of S. Step 2 is to map to the z-plane using z is equal to e to the st. Alright, and the form that we want to put this in is to have it in the product form. So h of z is going to be equal to some k of prime, the product of z minus, what did I call these before? I think it's on this page. Yep. Z minus e to the z k of t from k is equal to 1 to m divided by the product from k is equal to 1 to n of z minus e to the p of k of t. Alright, so we're using this product format, and we're going to map to the z using z is equal to e to the st, and that's right here. So if we want to get a 0 in the denominator at s is or a 0 in the numerator at s is equal to 0, s is equal to 0 is equal to 1. So this is h of z is going to be equal to k prime times, in the numerator, z minus 1, that is e to the st at s is equal to 0 for that guy. Then we're going to divide by z minus e. Again, we're going to plug in here where s is equal to negative 0.1 plus j 0.995 times t. And then we're going to have the other one, which is z minus e to the negative 0.1 minus j 0.995 t. Right, if we solve that out, that gets k prime is z minus 1 divided by z squared minus 1.6718 z plus 0.9048. All right, that's good. Okay, so mapped poles and zeros using that, and then this was actually number 3. Form the z transfer function. Form the transfer function, the h of z. And then the 4th step, determine k prime. Right? Now, to find k prime, we're going to compare the gain values of omega at omega n, which is 1, because this is omega n squared. So omega n is equal to 1. That's going to be the maximum value of this bandpass filter. To find the peak response of h of s, and we're then going to look at that same thing according to this function and set those equal at their maximum value. Therefore, the absolute value of h of j omega, so we're substituting in j omega into the s, at omega is equal to 1, absolute value, a little bit ambitious there, is going to be equal to, you can look at this thing, 1 divided by 1 squared plus 0.2 times 1 plus 1, and so that's, it equals 5. 5. Now we want to look at the other form, the h of z, and we want to try to find these and set them equal to each other. And so we're going to do the absolute value of h of z, evaluated at z is equal to e to the st, z is equal to e, and s is going to be at, so s is equal to j omega, where omega is equal to 1. So, this is all comes down to be 1. T. So this is z is equal to e to the j1t, because we have z is equal to e to the st, s is equal to sigma plus j omega. But for this particular instance, we're saying that sigma is equal to 0, which means we're only looking at frequencies along the j omega axis, and we are saying j omega is equal to, let me just say omega is equal to 1. So if we do all these substitutions, we get that, therefore, z is equal to e to the j omega t, where omega is equal to 1, so this is just jt, and t is equal to 1/2, so this is equal to j 0.5. We're getting a lot of substitutions and a lot of density of different dimensions that we can jump through. Because now we have related z to the s to the 2 dimensions of the s, which one of those is the Fourier dimension. And so we can relate all the way from the Fourier transform to the Laplace transform, from the Laplace transform to the z transform. Alright, anyways, if we plug in z is equal to e to the j 1t, which is equal to e to the j 0.5, and we plug that into this guy, we get that it is equal to 10.54 k prime. We want these things to match, so we just set them equal to each other. So we say, therefore, 5 is equal to 10.54 k prime. Therefore, k prime is equal to, let me see if I have it written down here, 0.4612. 0.4612. Whew. All right. So, given all of this stuff, we can now relate this all the way back to the original transfer function in terms of now z. So I'm going to erase these steps. I'm going to erase this stuff. And I'm actually just going to write the h of z beside the original h of s. See how much time we have left on it. So, h of z is going to be equal to 0.4612 times z to the minus 1, z minus 1, I'm sorry, not z to the minus 1, z minus 1 divided by z squared minus 1.6718 z plus 0.99048, but I'll just approximate. Okay, so now what's the next thing that we need to do? We're not done yet. Now we need to relate it in terms of our standard form, which the standard form again is h of z is going to be equal to the summation of oh shoot, now I'm drawing a blank. B of I, z to the negative I, divided by 1 minus the sum of a of j, z to the minus j, where j is equal to 1 to q, and I is equal to 0 to p. So now we need to turn it into this form, where again, notice we have the negative sign in the denominator. This is starting at 1, this is starting at 0. So if we rewrite this thing in terms of h of the negative z, without changing this, we're just factoring out a z. This turns into 0.4612 times 1 minus z to the minus 1 divided by 1 minus 1.6718 z to the minus 1 plus 0.9 z to the minus 2. So we took this z squared out front and we took this z out front. Now we did another step here because that actually leaves an extra z, but we know, let's see, does it? Factor out a z squared, factor out a z. So we did step number 5, which is to eliminate a z in order to keep the orders the same. And we can just do that because of the derivation we went through in the last video that showed they're equal. Okay, so now from here we can solve this down knowing that h of z is equal to y of z divided by x of z, the output over the input. So now I'm just going to skip to the end and say that y of n is going to be equal to, this gets distributed through, and so we have an x of the n times 0.4612 minus 0.4612 x of the n minus 1. And then these come to the other side, so then we have a plus y to the n minus 1 times 1.6718 minus 0.9 y n minus 2. Again, we're multiplying this here and then subtracting them over the other side. So this negative becomes a positive, this positive becomes a negative. The constants are out in front, so all we get is our filter delay function. And that's all the time I have on this recording.